Chapter 8 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Chapter 8, Part 1, Planets and Satellites. Continued. Part 1. The analogy between Mars and the Earth is perhaps by far the greatest in the whole solar system. So Herschel wrote in 1783, and so we may safely say today, after 60 further years of scrutiny. The circumstance lends a particular interest to inquiries into the physical habitudes of our exterior planetary neighbor. Fontana first caught glimpses at Naples in 1636 and 1638 of dusky stains on the ruddy disk of Mars. They were next seen by Hooke and Cassini in 1666, and this time with sufficient distinctness to serve as indices to the planet's rotation, determined by the latter as taking place in a period of 24 hours 40 minutes. Increased confidence was given to this result through Maraldi's precise verification of it in 1719. Among the spots observed by him, he distinguished two as stable in position, though variable in size. They were of a peculiar character, showing as bright patches round the poles, and had already been noticed during the 60 years back. A current conjecture of their snowy nature obtained validity when Herschel connected their fluctuations in extent with the progress of the Martian seasons. The inference of frozen precipitations could scarcely be resisted when once it was clearly perceived that the shining polar zones did actually, by turns, diminish and grow with the alternations of summer and winter in the corresponding hemisphere. This, it may be said, was the opening of our acquaintance with the state of things prevailing on the surface of Mars. It was accompanied by a steady assertion, on Herschel's part, of permanence in the dark markings, notwithstanding partial obscurations by clouds and vapors floating in a considerable but moderate atmosphere. Hence the presumed inhabitants of the planet were inferred to probably enjoy a situation in many respects similar to ours. Schroter, on the other hand, went altogether wide of the truth as regards Mars. He held that the surface visible to us is a mere shell of drifting cloud, deriving a certain amount of apparent stability from the influence on evaporation and condensation of subjacent but unseen areographical features, and his opinion prevailed with his contemporaries. It was, however, rejected by Kanowski in 1822, and finally overthrown by Beer and Madler's careful studies during 5 consecutive oppositions, 1830 through 39. They identified at each the same dark spots, frequently blurred with mists, especially when the local winter prevailed, but fundamentally unchanged. In 1862, Lockyer established a marvelous agreement with Beer and Madler's results of 1830, leaving no doubt as to the complete fixity of the main features amid daily, nay hourly, variations of detail through transits of clouds. On 17 nights of the same opposition, F. Kaiser of Leyden obtained drawings in which nearly all the markings noted in 1830 at Berlin reappeared, besides spots frequently seen respectively by Arago in 1813, by Herschel in 1783, and one sketched by Huggins in 1672 with a writing pen in his diary. From these data the Leyden observer arrived at a period of rotation of 24 hours, 37 minutes, 22.62 seconds, being just 1 second shorter than that deduced exclusively from their own observations by Beer and Mädler. The exactness of this result was practically confirmed by the inquiries of Professor Bakhuyzen of Leyden. Using for a middle term of comparison the disinterred observations of Schröter with those of Huygens at one and of Schiaparelli at the other end of an interval of 220 years, he was enabled to show, with something like certainty, that the time of rotation, 24 hours, 37 minutes, 22.735 seconds, ascribed to Mars by Mr. Proctor in reliance on a drawing executed by Hooke in 1666, was too long by nearly 1/10 of a second. The minuteness of the correction indicates the nicety of care employed, nor employed vainly, for owing to the comparative antiquity of the records available in this case, an almost infinitesimal error becomes so multiplied by frequent repetition as to produce palpable discrepancies in the positions of the markings at distant dates. Hence Bakhuyzen's period of 24 hours, 37 minutes, 22.66 seconds is undoubtedly of a precision unapproached as regards any other heavenly body save the earth itself. Two facts bearing on the state of things at the surface of Mars were then fully acquired to science in or before the year 1862. The first was that of the seasonal fluctuations of the polar spots; the second, that of the general permanence of certain dark gray or greenish patches, perceived with the telescope as standing out from the deep yellow ground of the disk; that these varieties of tint correspond to the real diversities of a terraqueous globe, the ripe cornfield sections representing land, the dusky spots and streaks, oceans and straits, has long been the prevalent opinion. Sir J. Herschel in 1830 led the way in ascribing the redness of the planet's light to an inherent peculiarity of soil. Previously it had been assimilated to our sunset glows rather than to our red sandstone formations, set down, that is, to an atmospheric stoppage of blue rays. But the extensive Martian atmosphere, implicitly believed in, on the strength of some erroneous observations by Cassini and Römer in the 17th century, vanished before the sharp occultation of a small star in Leo, witnessed by Sir James South in 1822, and Dawes's observation in 1865, that the ruddy tinge is deepest near the central parts of the disk, certified its non-atmospheric origin. The absolute whiteness of the polar snow caps was alleged in support of the same inference by Sir William Huggins in 1867. All recent operations tend to show that the atmosphere of Mars is much thinner than our own. This was to have been expected a priori, since the same proportionate mass of air would, on his smaller globe, form a relatively sparse covering. Besides, gravity there possesses less than 4/10 its force here, so that this sparser covering would weigh less, and be less condensed than if it enveloped the earth. Atmospheric pressure would accordingly be of about 2 1/4 instead of 15 terrestrial pounds per square inch. This corresponds with what the telescope shows us. It is extremely doubtful whether any features of the earth's actual surface could be distinguished by a planetary spectator, however well provided with optical assistance. Professor Langley's inquiries led him to conclude that fully twice as much light is absorbed by our air as had previously been supposed, say 40%, of vertical rays in a clear sky. Of the 60 reaching the earth, less than a quarter would be reflected even from white sandstone, and this quarter would again pay heavy toll in escaping back to space. Thus, not more than perhaps 10 or 12 out of the original 100 sent by the sun would, under the most favorable circumstances, and from the very center of the earth's disk, reach the eye of a Martian or lunar observer. The light by which he views our world is, there is little doubt, light reflected from the various strata of our atmosphere, cloud or mist-laden, or serene, as the case may be, with an occasional snow mountain figuring as a permanent white spot. This consideration at once shows us how much more tenuous the Martian air must be, since it admits of topographical delineations of the Martian globe. The clouds, too, that form in it seem in general to be rather of the nature of ground mists than of heavy cumulus. Occasionally, indeed, durable and extensive strata become visible. During the latter half of October 1894, for instance, a region as large as Europe remained apparently cloud-covered. Yet most recent observers are unable to detect the traces of aqueous absorption in the Martian spectrum noted by Huggins in 1867 and by Vogel in 1873. Campbell vainly looked for them visually in 1894, spectrographically in 1896. Keeler was equally unsuccessful. Joule holds that they could, with present appliances, only be perceived if the atmosphere of Mars were much richer in water vapor than that of the Earth. There can be little doubt, however, that its supply is about the minimum adequate to the needs of a living and perhaps a life-nurturing planet. The climate of Mars seems to be unexpectedly mild. Its theoretical mean temperature, taking into account both distance from the sun and albedo, is 34 degrees centigrade below freezing. Yet its polar snows are both less extensive and less permanent than those on the Earth. The southern white hood, noticed by Schiaparelli in 1877 to have survived the summer only as a small lateral patch, melted completely in 1894. Moreover, Mr. W. H. Pickering observed with astonishment the disappearance, in the course of 33 days of June and July 1892, of 1,600,000 square miles of southern snow. Curiously enough, the initial stage of shrinkage in the white calotte was marked by its division into two unequal parts, as if in obedience to the mysterious principle of duplication governing so many Martian phenomena. Changes of the hues associated respectively with land and water accompanied in lower latitudes, and were thought to be occasioned by floods ensuing upon this rapid Antarctic thaw. It is true that scarcity of moisture would account for the scantiness and transitoriness of snowy deposits, easily liquefied because thinly spread, but we might expect to see the whole wintry hemisphere, at any rate, frost-bound, since the sun radiates less than half as much heat on Mars as on Earth. Water seems nevertheless to remain, as a rule, uncongealed everywhere outside the polar regions. We are at a loss to imagine by what beneficent arrangement the rigorous conditions naturally to be looked for can be modified into a climate which might be found tolerable by creatures constituted like ourselves. Martian topography may be said to form nowadays a separate sub-department of descriptive astronomy. The amount of detail becomes legible by close scrutiny on a little disk, which, once in 15 years, attains a maximum of about 1/5000th the area of the full moon, must excite surprise and might provoke incredulity. Spurious discoveries, however, have little chance of holding their own where there are so many competitors quite as ready to dispute as to confirm. The first really good map of Mars was constructed in 1869 by Proctor, from drawings by Dawes. Kaiser of Leyden followed in 1872 with a representation founded upon data of his own providing in 1862 to 64, and Terby, in his valuable Areography, presented to the Brussels Academy in 1873 a careful discussion of all important observations from the time of Fontana downwards, thus virtually adding to the knowledge by summarizing and digesting it. The memorable opposition of September 5th, 1877, marked a fresh epoch in the study of Mars. While executing a trigonometrical survey, the first attempted, of the disk, then of the unusual size of 25 foot across, G.V. Schiaparelli, director of the Milan Observatory, detected a novel and curious feature. What had been taken from Martian continents were found to be, in point of fact, agglomerations of islands, separated from each other by a network of so-called canals, more properly channels. These are obviously extensions of "seas," originating and terminating in them, and sharing their gray-green hue, but running sometimes to a length of 3,000 or 4,000 miles in a straight line, and preserving throughout a nearly uniform breadth of about 60 miles. Further inquiries have fully substantiated the discovery made at the Brera Observatory. The canals of Mars are an actually existent and permanent phenomenon. An examination of the drawings in his possession showed M. Terby that they had been seen, though not distinctively recognized, by Dawes, Secchi, and Holden. Several were independently traced out by Burton at the opposition of 1879. All were recovered by Schiaparelli himself in 1879 and 1881 through 82, and their indefinite multiplication resulted from Lowell's observations in 1894 and 1896. When the planet culminated at midnight, and was therefore in opposition, December 26, 1881, its distance was greater and its apparent diameter less than in 1877, in the proportion of 16 to 25. Its atmosphere was, however, more transparent, and ours of less impediment to northern observers, the object of scrutiny standing considerably higher in the northern skies. Never before, at any rate, had the true aspect of Mars come out so clearly as at Milan, with the 8 3/4 inch Merz refractor of the observatory, between December 1881 and February 1882. The canals were all again there, but this time they were, as in many as 20 cases, seen in duplicate. That is to say, a twin canal ran parallel to the original one at an interval of 200 to 400 miles. We are here brought face to face with an apparently insoluble enigma. Schiaparelli regards the germination of his canals as a periodical phenomenon depending upon the Martian seasons. It is assuredly not an illusory one, since it was plainly apparent during the opposition of 1886 to Messrs. Perrotin and Tholen at Nice, and to the former using the new 30-inch refractor of that observatory in 1888. Mr. A. Stanley Williams, with the help of only a 6½ inch reflector, distinctly perceived in 1890 7 of the duplicate objects noted at Milan, and the Lick observations, both of 1890 and of 1892, together with the drawings made at Flagstaff and Mexico during the last favorable oppositions of the 19th century, brought unequivocal confirmation to the accuracy of Schiaparelli's impressions. Various conjectures have been hazarded in explanation of this bizarre appearance. The difficulty of conceiving a physical reality corresponding to it has suggested recourse to an optical rationale. Proctor regarded it as an effect of diffraction. Stanislas Munier of oblique reflection from overlying mist banks. Flammarion considers it possible that companion canals might, under special circumstances, be evoked by refraction as a kind of mirage. But none of these speculations are really admissible when all the facts are taken into account. The view that the canals of Mars are vast rifts due to the cooling of the globe is recommended by the circumstance that they tend to follow great circles. Nevertheless, it would break down if, as Schiaparelli holds, the fluctuations in their visibility depend upon actual obliterations and re-emergences. Fantastic though the theory of their artificial origin appear, it is held by serious astronomers. Its vogue is largely due to Mr. Lowell's ingenious advocacy. He considers the Martian globe to be everywhere intersected by an elaborate system of irrigation works, rendered necessary by a perennial water famine, relieved periodically by the melting of the polar snows. Nor does he admit the existence of oceans or lakes. What have been taken for such are really tracts covered with vegetation, the bright areas intermixed with them representing sandy deserts. And it is noteworthy in this connection that Professor Barnard obtained in 1894 with the great Lick refractor suggestive and impressive views, disclosing details of light and shade on the gray-green patches so intricate and minute as almost to preclude the supposition of their aqueous nature. The closeness of the terrestrial analogy has thus of late been much impaired. Even if the surface of Mars be composed of land and water, their distribution must be of a completely original type. The interlacing everywhere of continents with arms of the sea, if that be the correct interpretation of the visual effects, implies that their levels scarcely differ. And Schiaparelli carries most observers with him in holding that their outlines are not absolutely constant, encroachments of dusky upon bright tints suggesting extensive inundations. The late N.E. Green's observations at Madeira in 1877 indicated, on the other hand, a rugged south polar region. The contour of the snowcap not only appeared indented, as if by valleys and promontories, but brilliant points that were discerned outside the white area, attributed to isolated snow peaks. Still more elevated, if similarly explained, must be the ice island first seen in comparatively low latitude by Dawes in January 1865. On August 4, 1892, Mars stood opposite to the Sun at a distance of only 34,865,000 miles from the Earth. In point of vicinity, then, its situation was scarcely less favorable than in 1877. The low altitude of the planet, however, practically neutralized this advantage for northern observers, and public expectation, which had been raised to the highest pitch by the announcements of sensation mongers, was somewhat disappointed at the meagerness of the news authentically received from Mars. Valuable series of observations were nevertheless made at Lick and Arequipa, and they unite in testifying to the genuine prevalence of surface variability, especially in certain regions of intermediate tint, and perhaps of the crude consistence of boggy sierras, neither sea nor good dry land. Professor Holden insisted on the enormous difficulties in the way of completely explaining the recorded phenomenon by terrestrial analogies. Mr. W. H. Pickering spoke of conspicuous and startling changes. They, however, merely overlaid and partially disguised a general stability. Among the novelties detected by Mr. Pickering were a number of lakes, or oases, in Lowell's phraseology, under the aspect of black dots at the junction of two or more canals, and he, no less than Lick astronomers and Mr. Perrotin at Nice, observed brilliant clouds projecting beyond the terminator or above the limb while carried round by the planet's rotation. They seemed to float at an altitude of at least 20 miles, or about 4 times the height of terrestrial cirrus. But this was not wonderful, considering the low power of gravity acting upon them. Great capital was made in the journalistic interest out of these imaginary signals from intelligent Martians, desirous of opening communications with, to them, problematical terrestrial beings. Similar effects had, however, been seen before by Mr. Knoebel in 1873 and by Mr. Turby in 1888 at the Lick Observatory in 1890, and they were discerned again with particular distinctness by Professor Hussey at Lick, August 27, 1896. The first photograph of Mars was taken by Gould at Cordoba in 1879. Little real service in planetary delineation has, it is true, been so far rendered by the art, yet one achievement must be recorded to its credit. A set of photographs obtained by Mr. W. H. Pickering on Wilson's Peak, California, April 9, 1890, showed the southern polar cap of Mars as of moderate dimensions, but with a large, dim adjacent area. 24 hours later, on a corresponding set, the dim area was brilliantly white. The polar cap had become enlarged in the interim, apparently through a wide-spreading snowfall by the annexation of a territory equal to that of the United States. The season was towards the close of winter in Mars. Never until then had the process of glacial extension been actually, it might be said, superintended in that distant globe. Mars was gratuitously supplied with a pair of satellites long before he was found actually to possess them. Kepler interpreted Galileo's anagram of the triple Saturn in this sense. They were perceived by Micromegas on his long voyage through space, and the Laputan astronomers had even arrived at a knowledge, curiously accurate under the circumstances, of their distances and periods. But terrestrial observers could see nothing of them until the night of August 11, 1877. The planet was then within 1 month of its second nearest approach to the earth during the last century, and in 1845 the Washington 26-inch refractor was not in existence. Professor Asaph Hall, accordingly, determined to turn the conjecture to account for an exhaustive inquiry into the surroundings of Mars. Keeping his glaring disk just outside the field of view, a minute attendant speck of light was glimpsed August 11. Bad weather, however, intervened, and it was not until the 16th that it was ascertained to be what it appeared, a satellite. On the following evening a second, still nearer to the primary, was discovered, which, by the bewildering rapidity of its passages hither and thither, produced at first the effect of quite a crowd of little moons. But these delicate objects have since been repeatedly observed, both in Europe and America, even with comparatively small instruments. At the opposition of 1884, indeed, the distance of the planet was too great to permit the detection of both elsewhere than at Washington, but the Lick equatorial showed them July 18, 1888, when their brightness was only 0.12, its amount at the time of their discovery, so that they can now be followed for a considerable time before and after the least favorable oppositions. The names chosen for them were taken from the Iliad, where Deimos and Phobos, fear and panic, are represented as the companions in the battle of Ares. In several respects they are interesting and remarkable bodies. As to size, they may be said to stand midway between meteorites and satellites. From careful photometric measures, executed at Harvard in 1877 and 1879, Professor Pickering concluded their diameters to be respectively 6 and 7 miles. This is on the assumption that they reflect the same proportion of the light incident upon them that their primary does. But it may very well be that they are less reflective, in which case they would be more extensive. The albedo of Mars is put by Müller at 0.27. His surface, in other words, returns 27% of the rays striking it. If we put the albedo of his satellites equal to that of our moon, 0.17, their diameters will be increased from 6 and 7 to 7½ and 9 miles, Phobos, the inner one, being the larger. Mr. Lowell, however, formed a considerably larger estimate of their dimensions. It is interesting to note that Deimos, according to Professor Pickering's very distinct perception, does not share the reddish tint of Mars. Deimos completes its nearly circular revolutions in 30 hours 18 minutes, at a distance from the surface of its ruling body of 12,500 miles. Phobos traverses an elliptical orbit in 7 hours 39 minutes 22 seconds at a distance of only 3,760 miles. This is the only known instance of a satellite circulating faster than its primary rotates, and is a circumstance of some importance as regards theories of planetary development. To a Martian spectator, the curious effect would ensue of a celestial object seemingly exempt from the general motion of the sphere, rising in the west, setting in the east, and culminating twice or even thrice a day, which, moreover, in latitudes above 69 degrees, north or south, would be permanently and altogether hidden by the intervening curvature of the globe. End of Chapter 8, Part 1.